Hi, welcome back to another episode of Algebra in Words. In this episode, we're going to be looking at functions. If you're following along with the Roxwald-Krieger book, we're going to be in 8.1. And if you're following along in Algebra in Words 2, this topic starts on page 30. So let's get started. And first we want to talk about what is a function. So let me explain what a function is. A function is simply basically an equation and its data points which can be converted into a graph. But more specifically, let's look back at what we kind of know so far. What we've done so far is we've dealt with equations that might start off with y equals and then a number of variables. The one that I have up here is just a random quadratic equation that I chose. And once we get into function territory, all you're really going to do is replace the y with what's called f of x, which means this equation is a function of x. What does that mean? It just means x will have different values at different parts of the graph, and you substitute the values of x in and solve, and then whatever the equation comes out to be is what you would say f of x equals. Each time that you're solving or evaluating an equation for a certain value of x, then you might put that specific value of x here just to show you that you're evaluating the equation or the graph at that particular value of x. So a function just shows that the value of f of x or y just varies and changes at each value or point of x. So don't overthink it. It's a very simple concept. Now, it does get a little bit more specific though, because there can be certain types of equations and graphs that count or qualify as a function, whereas others may not. Okay, and the easiest way to be able to tell whether a graph or a function, or I should say an equation, is a function or not, is to look at its graphical representation. So what I have on the board to start is 4 basic graphs. One is a linear graph, one is a parabola, one is a sideways parabola, and one is a cubic. So the easy way to determine whether an equation and a graph is a function or not by definition is to use what's known as the vertical line test. The vertical line test means you draw a vertical line through the graph, and if you're able to draw a vertical line through any graph at any point, and it goes through the graph twice, then it disqualifies it by definition as being a function. And I'll explain why that is in a second. But for now, let's test each of the 4 graphs to see if they're a function. So let's do the vertical line test here. And it goes through the graph one time, and there's no other place in this graph that it can go through twice. So is this linear equation and graph a function? We would say yes. I'm just going to put y for yes. Okay, what about the parabola right here? We could draw the vertical line through here, and it goes through the graph once. We could draw it through here, and again it goes through once. There's no other place on this graph where the vertical line would go through this graph more than once. So is this a function? Yes. Let's come to the sideways parabola. And this is really the exemplary situation. So first of all, what if I do this? A vertical line through. Well, clearly it goes through the graph more than once. It goes through twice. Automatically that disqualifies it as a function. So if we said, is this a function? We would say no. Now keep in mind, suppose we were to draw the vertical line through here, and you could say that it goes through the point or the tip, the vertex, once. That doesn't mean that it's a function. The question you have to ask is there a place on the graph that you can draw a vertical line for it to go through the graph more than once? That's what you're testing for. So clearly when we did it over here, it disqualifies it as a function by definition. And finally, what about this one? It's a cubic. And if we draw the vertical line, whether here, or here, or here, it only goes through once, so that means that this is a function. We could say yes, it's a function, or you could write function. Now, the vertical line test that we just did actually exhibited something, exhibited the definition in a conceptual graphical way, but we could actually answer the question without the graphs. So to get closer to the definition of a function is this. A function is an equation or a set of data points in which there is only one ordered pair, or I should say, only one value of x for every y. Okay, so only one value of x for every y. If we're looking at that graphically, let's tie that into the vertical line test. Let's go right to this one where it fails. Okay, only one x for every y. Now, in this case, suppose that this value of x is, let's say, 2. Okay, 1, 2. There's a point here and a point here. They both have the value of, they both have values of the same x. So that would disqualify it as a function because there is two x's and there can only be one x. Alright, so let's look at the data, let's look at some actual data points. Okay, and if we're looking at this first set of data points, and let's just call them points on a graph, x and y points, there's a 1 and a 2, okay? And basically the point is, what we're looking for is, are there multiple values of x? And the answer is no. But what about when we look at this set of data? This is just another random set of points that could be graphed, okay? Notice that we have -3, 0, okay? But then we might have -1 and 1, and -1 again with another 1, okay? And again, the point here is, the instant that you see more than one x value on the same graph, that disqualifies it by definition as being a function. So if you're given data points, that's what you're looking for. Repeating values or points with x. And you simply can't have that. Now, that's basically all there is to it. You can have the same value of y and it still be a function. And one example of that is if we look at this parabola. Okay, notice that in this parabola, each value of x is unique. There are no duplicate values of x. However, are there any duplicate values of y? There's many duplicate values of y. You could look here, right, where y is 0, and there's a value of x here and a value of x here, where the values of x's are different, but the values of y are the same. So just to reiterate that, by definition, for the definition of a function, there can only be one unique point for x, but there can be multiple points of the same y, and it still be considered a function. Okay, so there's four types of things, and four types of things you might have to answer or solve in regards to being introduced to a function. One is the vertical line test, which we just looked at. Another one is evaluating a function for a given value of x. We'll do that in a second. That basically involves plugging in a value and solving. Another thing is given a number of data points, to evaluate just the data points to determine whether its representative graph or function would be a function or not. That's sort of what we just did here. And finally, another thing you might have to do is, you could be given a function and be asked to tell what the domain is of that function and of that graph. And I'll explain that in a few minutes. So I'm going to erase the board and put a couple problems up. Okay, so I have two problems on the board. And for problems like this, you're going to be given a function and given a certain value of x, and it's going to ask you to evaluate the function with the given value of x. These are very easy. All you have to do is plug in and simplify, and that's your answer. So let's look at the one above. Find f of x for the function f 5 minus 3x when x equals -4. Okay, so watch what I do here, just so we go through the proper steps. I'm going to do f of, the way you would say this is f of -4 equals, and now I'm going to plug in -4 for x. So rewriting the 5 minus 3 and substituting the -4 in for x, and now I'm just going to simplify. Let's follow order of operations. 3 times -4 is -12, and so I'm just going to do, to show all the steps, 5 minus -12, and minus on minus is plus, so 5 plus 12 is going to be 17. And that's the answer. The answer is 17. If we wanted to give that in a point form, we could show it like this. -4, 17, where 17 really represents the y. That's all there is to it. I have another one. F of x is equal to x cubed when x equals -2. So let's show it by saying f of -2 equals x cubed, and now I'm just going to substitute the -2 in for x. Make sure you keep the sign in the parentheses. Although for cubes it doesn't matter, but we want to make sure we do the right thing anyway. Okay, and evaluate, that means simplify. -2 raised to the power of 3 equals -8. So the answer is -8. And if we put that in point form, we could show it as -2, -8, because it does represent a real point on a real graph represented by the function. So again, to summarize this, when it says to evaluate, they'll give you a value of x. They might give you multiple values of x. Just substitute each value in one at a time and solve, and then do the next one. These are the simplest type of problems you could do. It's just plugging in and simplifying. So I'm going to pause the video and then put up another problem. The next problem that I have on the board is f of x is equal to -2x plus 1. If you're following the Roxwald-Krieger book, this would be number 44 in section 8.1. And this problem asks you to, they give you a function and they want you to sketch the graph of this function. This is very easy, and actually this is nothing new. Before we do the actual solving and figuring out, by now if you looked at the function and I asked you what type of equation or graph do you expect from this, hopefully you could tell that this looks like a linear equation, right? It's x with the degree 1, and this is going to make a line. Okay, you've done this already. It's basically involving making up a table and filling in, and so we're going to set up a table, and then we're going to evaluate, sort of like we did in the last problem, but just for a number of points. And we could do it for 3 points, you could do it for more points, and then you'll have the points, and then you can graph it. So let's do that by setting up a basic table, and in this case, let's use 0, 1, 2, and let's also do -1. Okay, now what we're testing for here is well, we're just evaluating by plugging these x values in one at a time. This is really an exercise of evaluating like the last problem, and then we'll just generate points. We do just want to be aware that to see if we get any points that would have multiple points of x, but since we're starting with x and plugging in, that shouldn't happen here. And we already know that this is a linear equation, so we already know that that's not going to happen. Alright, so let's evaluate, and we'll do it properly by putting in 0 in for x like this. Alright, 0 times 2 is 0, and that leaves us with 1, so let's put 1 in here. And so what does that mean? F of 0 is 1. Okay, then let's do the next one, f of 1, where I substituted 1 in for x, and I also put the 1 in for x there. Okay, so negative 2 times 1 is negative 2. Negative 2 plus 1 equals negative 1. And I put that in the chart. Now let's do f of 2. Substitute negative 2. That's positive, sorry. Let's substitute 2 in for x plus 1. Negative 2 times 2 is negative 4. Negative 4 plus 1 equals negative 3. And let's put negative 3 in. And then we have f of negative 1 Negative 2 times negative 1 is positive 2, plus 1 is positive 3. Okay, so we found 4 points from this function by evaluating at 4 different values of x. So now I'm going to erase that, and then we're just going to graph. So I set up a graph, and all we're going to do is plot the 4 points, which I'm sure you know how to do at this point. So 0, 1, and 1, negative 1, which would be down about here, and 2, negative 3, so let's go over 2, and go down 1, 2, 3, and then negative 1 and positive 3. Negative 1 and up 3. 1, 2, 3. Okay, and those points all fall in line, so that all makes sense. Draw the line through. So we just graphed the function given. So that's how you do those problems. To summarize, make up a table of 3 to 4 points, all of x only, different values of x, substitute the values of x into the function, do them individually, separately, simplify, solve, put the answer for y back in the table. You could also actually call this column, the books will probably call that f of x, but truthfully, they're the same thing. And then you just plot the points on the graph and graph. Okay, so I'm going to pause the video and we're going to look at another problem. Okay, this brings us into another type of question that relates to functions and graphs now, in which we're going to be asked to give the domain and the range of each function or graph. Now, if we have the graph of each function, or of a function, we can use the graph to answer the question of the domain and the range. So first of all, just to give some background on domain and range, what is domain? Domain means all the possible x values of a graph. And range means all the possible y values of the graph. Now, the interesting thing about domain and range that you need to know is, normally we look at the x and y values together, but domain and range is looking at the x values separate from the y values. So what I have on the board is 3 problems and 3 graphs, and we're going to use those graphs to determine the domain and range of each. Again, if you're following along with the Roxwald-Krieger book, then what I have on the board are numbers 77, 78, and 81, if you want to follow along with those. So let's look at the first one, and it's sort of like a half circle. Okay, now what I'm going to do is I'm going to write D for domain, and all we want to do is try to use blinders and only look at what the possible x values are. So we're only scanning in this case like left to right. The vertical points have nothing to do with this. We're only looking at the domain, the x values. So let's start where the graph starts on the left. It starts at negative 2 and it ends at positive 2. Notice that on this graph, they start and end with points. There's not arrows the way that this has arrows. So since this starts and ends with points, they're like the hard start and finish. So anyway, long story short, the domain for this graph is going to be -2 to +2. But now we're going to write this like this. We're going to show it as -2 is less than or equal to x, which is less than or equal to 2. The form that this is written is known as a compound inequality. We'll get to that in another episode. But basically, this is how you should be writing the domain and the range for now. Basically, the x in the middle, and compound inequality is made up of two smaller inequalities. So, for example, if you look just at this portion, -2 is less than or equal to x. If you flipped it, you could read it as x is greater than or equal to -2. So, right, if you're looking at thinking of x as the x values in the domain, x is greater than or equal to -2. It's greater than because the dot means it's inclusive. And it ends here as the highest. So if we look at x is less than or equal to +2, whereas this was x is greater than or equal to -2, so greater than here and less than 2 here, that's what makes this make sense. Okay, so I think I'm rambling on a little bit more than I need to about that. But anyway, let's also now apply the same thing to the range. Okay, and now when we're looking at range, we're only looking at the vertical aspect of the graph. So only up and down. Okay, so starting here at the lower portion, what is the lowest value of y here? It's 0. So we could say 0. And now let's write less than or equal to y. And then we'll put the highest value. And what does it go up to? In this case, it goes up to 2. So we're going to say y is less than or equal to 2. So in summary, the domain of this graph is -2 is less than or equal to x, which is less than or equal to 2. And for the range, the y values, we show it as 0 is less than or equal to y, which is less than or equal to 2. And just so we have this proper, let's just make this a colon. And let's look at the next one. Okay, let's look at the next one a little faster. We have this graph here, and so let's just go right to the domain. We're looking only at the horizontal, all the possible horizontal points. So starting here, -2, less than or equal to x. And where does it end? It ends at 2, coincidentally, like the last one. So the domain is -2 is less than or equal to x is less than or equal to 2. Let's look at the range. Let's start with the lowest possible point of y. Down at the bottom, -3. -3 is less than or equal to y, which is less than or equal to, what's the highest value of y here? 3. And that's it. Let's look at the last one. Notice it's a parabola. Let's start off with the domain. What are all the possible values of x? Very important that you notice the difference between this one and the other ones. These have arrows on the ends. No, sometimes we don't draw it with the arrows, but we should. And this means that it's extending on and on forever. So even though it looks like it's kind of going upward, remember, it's still going to the left and right towards infinity. So the way that we're going to write the domain the way that we're going to answer domain is, you could say all values of x, you could also say all real numbers. There's also a little symbol you can use for that. if you can see it here, it looks like that. It almost looks like an R with two lines, so you could write that symbol to represent all real numbers if you want. Then let's look at the range. Okay, well, we know that in this case it has a hard lower limit. So I have that here. I don't have this drawn to the same scale as the other graphs, keep in mind, but let's assume that this point is y is -1. So the lower point is -1, and then we're going to say less than or equal to y. And what is the highest value that y can be? Well, it does have a hard beginning at the bottom, but it goes up and on forever. So we're going to say less than or equal to, we can say infinity here. But another way that we can say actually the same thing is we can just sort of reverse it and simplify it as y is greater than or equal to -1. And hold on. Y is greater than or equal to -1. And that basically summarizes it, where we have -1 here, and if the range of y values is greater than or equal to that, then that includes all numbers above -1, including -1. Okay, and the last set of problems we're going to look at are dealing with also looking at the domain when you're given the equation form of functions. So the last one we looked at finding the domain and range with a graph, but now we're going to do it with the equations. And the strategies are very simple. There's three things you need to know. The first thing is you're looking for denominators that have x in it or radicals with radicands with x. So the strategy is if there's no variable in the denominator or a radical, it's automatically all real numbers. So I have three examples up. And if you're following with the Roxwald book, you can find these on page 534. In the first one, is there a variable in the denominator or a radical? No. So automatically the answer is all real numbers. It's as simple as that. In the next one, again, is there a variable in the denominator or a radical? Well, there is a variable in the denominator in this case. When there's a variable in the denominator, you're going to do the same thing as if you were solving for an extraneous solution. Set the denominator equal to 0 and solve for x. So we're going to set x plus 1 equal to 0 and solve. -1, x equals 0, and in this case, the domain is all real numbers except for the extraneous. So all real numbers except 0. And that should make sense because we find the extraneous by setting the denominator equal to 0 to find out what x needs to be to make the denominator equal to 0. So again, in summary, when there's a variable in the denominator and you're solving for the domain, set the denominator equal to 0, solve for x, and the domain is all real numbers except what you solved the denominator equal for x. And now let's look at the last one, which has a radical and x in the radical. The strategy for finding the domain when there's x in the radical is a little different than the other ones. And what you have to do is set the radical greater than or equal to 0. So that's what we're going to do. We're going to take the radicand itself, 2 minus x, and set it greater than or equal to 0. That's what you do to find the domain of any radical. Set it greater than or equal to 0. Only the radicand, not the whole radical itself. And then solve for x. So in this case, we're going to add x to both sides. And we're going to get 2 is greater than or equal to x. But let's flip it so that we have x on the left and the number on the right. And then make sure we also change the direction of the inequality symbol. So it's going to be x is less than or equal to 2. And so the answer is this. That's the domain. The domain is x is less than or equal to 2. And you could test that by taking 2 and substituting it in. And the basis behind that strategy is keeping in mind that at least for a radical of even root, such as 2 or 4, you can't have a radical that's less than 0, meaning a negative, because that will give you a non-real number or an imaginary number. So that's why setting the radicand greater than or equal to 0 helps you find the domain, at least for even roots. So anyway, that concludes the lesson on functions. Please comment, rate, and share, and also check out content on my other platforms, which I don't have up yet, but will soon. And I'll see you in the next video.